Imagine a computer counting faster than you can read the digits. And you think, given enough time, it could just keep going. Forever. But it can't. There are specific exact limitations for every computer on Earth that they can't surpass. And past those points, getting to a bigger number is about reconsidering what a number even means to a machine. So today we're finding the biggest number a computer can make. Every computer, underneath everything, every app, every game, every video you've ever streamed, is doing exactly one thing. Flipping switches called transistors on and off, 1 or 0. We call that a bit. Your phone, your laptop, basically anything built in the last decade is what's called 64-bit. That means the processor, or the CPU, has 64 of these switches sitting in a row, ready to represent a single number at once. That row is called a register. Think of it as the computer's scratch pad, the physical space where numbers are stored and simple math actually happens. So what's the biggest number you can make by flipping 64 switches on or off? Don't overthink it, just flip every switch to 1. Converting from binary, that's 2 to the 64. In base 10, that's over 18 quintillion. That's the ceiling. Not because the computer gets tired or something, but because there's physically no more room. Every switch is already on, and there's no hidden 65th switch anywhere. If you try to add one more, the number won't get larger. It'll simply overflow and wrap around back to 0. 18 quintillion sounds enormous. It's more than the number of grains of sand on every single beach on Earth, several times over. But it's nowhere close to enough for certain applications. Say if you're a physicist trying to measure the distance between galaxies or count the number of atoms in a star, 18 quintillion is just a rounding error. So what's the fix? The counterintuitive solution is that we actually don't need more switches, only a more clever system to use the ones we already have. You've actually already learned the trick. You just call it scientific notation. Instead of writing out 700 billion, you write out 7.0 times 10 to the 11th. Right here. You're not storing every digit. You're only storing two things. 1, a base number, and 2, an exponent, which tells you how far over to shift the decimal point. Computers do exactly this. It's called floating point arithmetic, specifically a standard called IEEE 754 double precision, and it's running under the hood of almost every scientific calculation, video game physics engine, and piece of software that touches decimals. Here's the trade-off. That same 64-bit space gets split. Some bits store the base number, called the mantissa, while the rest store the exponent. You're sacrificing the exact digits for absurd reach. Using this method, a standard 64-bit computer can represent numbers up to roughly 1.79 times 10 to the 308th power. For context, the number of atoms in the observable universe is roughly 10 to the 80th power. This floating point ceiling is 10 to the 308th. That's over 200 orders of magnitude larger. That's not bigger by a little. We are so far past atoms in the universe, it's almost a joke. But, and this is the important part, try to go even one number past that ceiling, and the computer doesn't give you a bigger number. It just gives up entirely. It just prints out the word infinity. It's in error state wearing a value's clothes. The machine is telling you, I have officially run out of scale to represent this. So is that it? Is 10 to the 308 the biggest number conceivable? We've been playing by the hardware's rules this whole time. What if we cheat? Nothing says the number has to live in just one register. What if you chained a bunch of them together, used 10 registers, 1,000, a billion, stringing along all of them together to represent one single gigantic number? This is called arbitrary precision arithmetic. You might know it as big int if you've ever hit an overflow error and tried to fix it. Instead of asking the hardware for a fixed sized box, a register, you ask the software to build boxes for as long as you need, chaining memory addresses end to end. And when you do this, the ceiling doesn't become the processor anymore. It comes from something a little more mundane, how much memory you have. Let's do the math. Let's say you had 16 gigs of RAM. I'm not sure how you'd get it in this economy. Each byte having 8 bits can represent 2 to the 8 or 256 different values. So if you dedicated every single byte of RAM to storing one number, the largest value you could represent is roughly 256 raised to the power of 16 billion. I'm not gonna pretend that number means anything intuitively. This isn't a number in the way you think of numbers anymore. It's a number defined entirely by however much hardware you're able to throw at it. Now, let's act like OpenAI and Oracle for just a moment and throw more RAM at the problem. Instead of 16 gigabytes, what if you threw everything at it? Let's take this as far as physics will legally let us. Forget 16 gigabytes, what if you converted the entire observable universe, every atom, every particle, every scrap of matter and energy, into one enormous hard drive dedicated to storing a single number? You might assume the answer is infinite, more space, more memory, forever. Well, wrong, I said observable universe, which has a finite diameter known as the Hubble horizon. And if you haven't caught it, this is the part of the video where you go from computer science over to physics. There's a hard limit on how much information you can cram into a given space before it collapses into a black hole under its own information density. It's called the Bekenstein bound, named after Jacob Bekenstein, and it comes straight from thermodynamics, the field of physics that deals with entropy, heat, and energy. The idea, roughly, is that information isn't free. Every bit you store has to be physically encoded into something. And once you pack enough bits into enough energy in a small enough space, gravity takes over and crushes it into a black hole. Past that point, you're not storing any extra information, you're just feeding a black hole. When physicists run this calculation for a region the extent of the observable universe, the answer comes out to roughly 10 to the 122nd power bits. Make sure you understand what I'm saying. 10 to the 122 is not the final answer. It's 10 to the 122 bits of storage in all of reality. Every one of those bits could be a 0 or a 1. And when you use every single one of them to represent the largest possible number, you get 2 to the 10 to the 122. Is the biggest number that can ever physically actually exist anywhere, under any circumstances, everything, everywhere, all at once. Not the biggest number mathematically. Math doesn't have a ceiling. You can always add 1. But the biggest number that could ever be written down, expressed, represented, computed, stored by anything made of matter or energy in this universe. That's it. That's the wall. Reality itself runs out of room. Subscribe if you want more of these videos where I take one dumb or curious sounding question and chase it to the extent of what's physically possible. I'm really trying to develop a curious fan base by the time I get to college in the fall so that things can be more frictionless when I get there. But for now, that's everything. I really hope you enjoyed. I appreciate you watching. It's 12:28 a.m. Have a great night.